Hello again, IB juniors. We are about to approach some of my favorite stuff in the IB curriculum. I'm talking about the geometry of curves. Now, we've been talking a lot about slopes of curves and, tangents and normals. And in the last notes, we were specifically talking about places where derivatives were equal to zero. And I called those critical points, critical values for x. We're going to start talking about more specifics about what is going on when the first derivative equals zero. These notes are called stationary points. So before we get into practice, we've got to talk about some vocabulary. A stationary point of a function is any point where the first derivative equals zero. Why do we call it stationary? Because the slope there is equal to zero. Remember, if you called the position function, say f of x, then its derivative would have been the velocity function. So everywhere where the derivative equals zero, you would have had a velocity of zero, therefore not moving. So that's one of the reasons why we call the places where the first derivative equals zero a stationary point. Now, a stationary point could be one of three things to any curve. It could be a global minimum. That means it's the lowest point on the curve. It could be a local maximum, which means it's the highest point in its general surroundings. We always find this at the top of a bump. Looks like this. The local max would be here. A local minimum is the exact opposite of a local max. It's a place that's going to be found at the bottom of a bump. Now, it's not necessarily the lowest part of the curve, but if you were standing right here and looked around, all the points would be generally above where you were. And just like how there can be a global minimum, meaning the lowest point on a curve, there can also be a global maximum, the highest point on a curve. Now, not all curves have global minimums or global maximums, so we're really going to stick to the terminology of local minima, local maxima. We call them local extrema. So other than a minimum and a maximum, one other place where the first derivative can equal zero is called a stationary inflection point. And that, we've said that term before, and we saw it happen like this, like a cubic function. This place right here in the middle is a place where you do have a slope of zero. So it is stationary, but it's not a minimum, it's not a maximum. So we call it a stationary because slope is zero. Inflection point. Inflection tells you it was not a min or a max. This is when the first derivative equals zero, but it is not a turning point. A turning point is a place where your graph goes from increasing to decreasing or from decreasing to increasing. In the last set of notes, we specifically talked about increasing and decreasing. What I didn't tell you was every time you had a sign change on your sign diagram, that x value is known as a turning point. Okay, so here we have a graph, and I've just got some points on it for you, and I believe the intent was that they would have been called points A, B, C, D. I'm not quite sure. I clearly stole this picture from the book or from a book or from the internet or somewhere, and I believe I stole this stuff from the book as well. Originally there was a picture that went along with these, and I didn't like it, so here's a different one. Alrighty, so in this picture here, this point is a local maximum. It's a local maximum because all the points around it are definitely below it. This happens to be a turning point. Well, as it turns out, every local max or local minimum will always be a turning point. Now down below, I have the sign diagram that matches up with this curve showing you its slopes. You see the slopes to the left of -2 were positive, and the slopes to the right of -2 were negative. This point is the place where the graph stopped decreasing and then started increasing, negative slopes to positive slopes. It is a local minimum, but it is also a turning point. Gonna get lazy here, just do turning PT. And then this one, if you look at your sign diagram, went from increasing to, well, increasing again. Now in between you had a slope of zero, so it was stationary right here. But because I didn't have a sign change, this was not a turning point, therefore it is a stationary inflection point. A lot of vocabulary in this lesson, and more coming up. So down below, we just have a breakdown of what's going on your sine diagrams. So, there's 3 rows because there's 3 types of stationary points, 3 times when the first derivative could equal 0. You could have a sine diagram that is showing you was positive and is now negative. You automatically know that's a local max because it had to have been going up and then going down. It didn't have a choice, and that's what you're seeing right here. It could have been a local minimum, meaning it was decreasing. Ooh, my blue pen is not cooperating. Come on, blue pen. There we go. It woke up. Decreasing and then increasing, which is what you see happening over here. See, we know the general shape of the curve just by knowing the sign, S-I-G-N, of the first derivative. And then lastly, down here, just wrapping up the review of what was going on right there, is stationary inflection. And it's any place where you had a stationary point, and notice that this line above point A is not dotted. So this is not a vertical asymptote. This is not a discontinuity. It's a place where you were stationary. And notice to the left and to the right, same sign, same thing here, to the left and to the right, same sign. So this one was showing you was positive slopes and then positive slopes. This one is showing you negative slopes and then negative slopes, which is exactly what you see going on right here. Okay? Okay. So now that we got all the boring business out of the way, implying the rest is awesome, we are going to find and classify all of the stationary points of this polynomial. Now, the fact that I said polynomial immediately clues you into the fact that it has no discontinuities. I mean, polynomials are smooth. They have no discontinuities. So we just lean on the skills that we learned in our last lesson. We need to figure out where the first derivative equals 0, because that's what it means to be a stationary point. So first we have to find our first derivative. Using power rules all the way across the board, it's going to give us 3x squared minus 6x minus 9. We set this equal to 0, and we're going to have to factor it if we want to figure out where its stationary points are. I see a GCF of 3. Let me pull the 3 out just to see what I'm working with here. X squared minus 2x minus 3. And yep, that factors. 2 numbers that multiply to negative 3 and add to negative 2 will be negative 3 and positive 1. There. So we have two, I did this on the side of the board and realized you couldn't see it on camera, 2 stationary points, one at x equals negative 1 and another at x equals positive 3. So we have found the stationary points. Now we have to classify them. And the only way we can classify them is by using a sign diagram and checking the signs, aka whether or not the slope is positive or negative to the left and to the right of these values. So here's one at negative 1, here's one at positive 3, and let's check. Let's plug in like negative 2. Right here, it's going to be negative times negative, positive. Let's check a number between these. Oh, no, really easy one, 0. If you plug in 0, you get positive times negative. And a number like 4 is going to give me positive times positive, positive. So just to help you out with what's going on in the sign diagram, hopefully you'll start to see things like this happening in your head. To the left of this number, I have positive slopes. It flattens out. Then to the right of this number, I have negative slopes until it flattens out. And then I have positive slopes again. Clearly, here and here are both the same kind of stationary point. Notice the sign change from here to here. This is going to be a local maximum. And notice the sign change from here to here. This is going to be a local minimum. So they are both turning points. And x equals negative 1 is a local max. And x equals 3 will be a local min. And there you have it. See, the blue and the green that I've used here is not necessary. I would like for you to be able to do that in your head, and you will be able to after some practice, okay? So there you go. Next example. Let's get away from the really, really easy stuff, polynomials. Ugh. Let's do some more fun stuff. How about some stuff that is going to require us to use the product rule? Yeah, buddy. So let's use the product rule. U is x minus 2. V is e to the negative x. U prime is just the derivative of this linear, so it's 1. And v prime, good, we get to practice with some exponentials. Remember, the derivative of every exponential follows this pattern. You write the exponential, and then you multiply by the derivative of its exponent, which happens to be negative 1. There. Product rule. F prime of x is equal to u prime v plus u v prime. I'm just going to fill it out. Gives me u prime, that one's easy, v plus u v prime. Okay. Let's see. Let's play some games here. We know we're gonna have to set it equal to 0. Let's see. We have e to the negative x, and then if I were to distribute this e to the negative x, I would have minus e to the negative x times x minus 2e to the negative x. So you're asking, how do we figure out where that equals 0? Well, just like the last example, factoring is the solution. We're going to have to factor. So for this one, what I'm seeing is a GCF of e to the negative x. So we pop that bad boy out of there, and it's going to leave us a 1 from here, a minus x from here, and a minus 2 from here, which does simplify to 1 minus 2 is negative 1. Negative 1 minus x, if that's a little bit confusing, hold on, something went wrong. What went wrong is the question. There it is. I bet you were screaming at your monitors. I didn't distribute a minus sign. Negative e to the negative x times negative 2 is positive. There it is. Much better. I was going to say, I didn't like the way that looked. Let's try that again. There we go. Okay. Much easier to work with. So we're wondering, where does this equal 0? Well, good news is exponentials that have not been shifted up or down never equal 0. You can't raise a positive number, which e is, to any power and ever get the answer 0. So this never equals 0. So the only place where we have a critical value, the only place where our first derivative equals 0 and therefore a stationary point, is when x equals 3. So our sign diagram is remarkably easy for this one because it has a single point on it. No need to get big here. There. So let's plug in a number, to the left of 3. How about the number 0? Well, e to the 0 is 1 times 3. Yeah, that's positive. And how about I plug in a number to the right of 3, like 4? Well, e to the negative 4 is still a positive number. And 3 minus 4 is a negative number, so positive times negative gets me this. So what you're seeing in your head is this shape again, going up to the left of 3, going down to the right of 3. Therefore, I have a turning point, which is a local maximum at x equals 3. X equals 3 is a turning point, and local max. There it is. Okay. Moving on. We've been asked to find the greatest and least value of this polynomial on a restricted domain. That means we have endpoints. Well, guess what? Endpoints, but technically, are critical values. Now, they're not necessarily stationary points, but they are critical values. We have to test them because, the left side of a curve could be the lowest or the highest point, and the same logic goes for the right side of a curve if it has hard endpoints. So when we construct our sign diagram, it's not going to have arrows on the left and right. It's going to have numbers on its left and its right. Find the greatest and least values, and I can do this using calculus without a graphing calculator. And the way we do that is with derivatives. Why, Mr. M? Well, because if you know you're increasing from one point to another and then decreasing afterwards, the point in between had to have been a local max. It may have also been the global max. That's just something you have to test for. And the same logic goes for if you were decreasing on the left side of a number and then increasing on the right side of a number, you have found a local minimum. It's a low value, and it might actually be the lowest value. Now, the fact that this is a cubic tells me that if I didn't have endpoints, there would be no such thing as a global max and a global min because it points up and down forever. But we will have a global max and a global min on this domain. I think we will. I mean, that's what they're telling us to do, right? Unless, of course, two of them have to have the same value. Let's find out. Y prime, first derivative is 3x squared minus 12x. And just like we were doing before, we're going to set it equal to 0 and factor. GCF of 3x will come out, leaving me an x minus 4. So I have two critical values, and they're both on this domain. I have one when x is equal to 0, because 3 times 0 is 0, and I have another at x equals 4. So we make our sign diagram, and you know what? I'm going to use this space here. So I'm going to draw my sign diagram down here. Whoops. Even after I said I wasn't going to have arrow on the end, what'd I do? Put an arrow on the end. Habit. Hard endpoints, -2 and +5. Picture not drawn to scale, because who cares? I just wanted to make sure I have some space. There. My two critical values between my two endpoints. Now let's see what's going on in derivative land, shall we? The number between -2 and 0 will be -1. Plugging it in right here gives me negative times negative. Positive. Gotta make sure I don't mess up because I'm writing in pen. A number between 0 and 4, I like 1. Positive times negative. Number between 4 and 5, kind of a pain in the butt, but 4.5, no big deal. Positive, positive. Okay, now, remember, this is an endpoint, and this is an endpoint. And I'm increasing away from this point. That means, by definition, this point right here must be lower than this point. It doesn't have to be lower than that point, though. So we're increasing for a while. We have found a local maximum, and then we're going to decrease for a while. Picture not drawn to scale because I actually don't know what the y values are. We're decreasing to there, and then we are going to increase again. And somewhere, again, picture not drawn to scale. I'm not drawing that as the highest or anything. I'm just drawing it. What I'm showing you is we actually have 4 different values we have to check. Now, we know this is a local max, and we know this is a local min. But we don't know if this point is higher or this point is higher. And we don't know if this point is lower or this point is lower. So we have to check them both. Actually, we have to check them all, excuse me. Okay, let's see what's going on at the end point at -2. We're plugging in right here to find its y value. It's going to give me -2 cubed minus 6 times -2 squared plus 5. I will save you all the calculations, and I will tell you that equals -27. Now we plug in 0. That one's easy. 0, 0, 5. I mean, I don't even have to do any work for that. Everywhere there's an x just disappears, right? Now let's plug in 4. Okay, plugging in 4 is going to give me 4 cubed minus 6 times 4 squared plus 5. Once again, I will save you the time of grabbing the calculator and tell you that it is going to give you -27. Whoa! These 2 points have the same y value. That means technically this curve does not have a global minimum. It does have a least value of -27 though. Interesting. Now let's plug in the last endpoint, plugging in 5. It's going to give me 5 cubed minus 6 times 5 squared plus 5. Man, that's a lot of 5s. Anyway, it gives you negative 20. So, again, picture not drawn to scale. This has a negative y value. This one doesn't. So this point is actually higher than this point. So what do we know? We know that at x equals 4, 0, at x equals 0, we have a global max of y equals 5. And at x equals negative 2 and x equals negative 4, we have the least value, y equals negative 27. So I can't call it the global minimum because that implies it is the lowest of the low. And since they're equal, you can't say one is lower than the other. And there you have it. Okay, this last question. This last question I included in the notes to try to help you out with those IB level questions that some of you have been doing what I wanted and getting on Zoom with me to learn how to do the hard ones. And others of you, unfortunately, I doubt actually know what's going on. There's a handful of you that might, but my strong feeling is that a majority of you is just saying, oh well, I'll just take the L on that and I'll copy the answer from somebody or somewhere or whatever, and it's not going to affect me. Wrong. Because next year you are going to be held accountable with tests. That's right. I am going to test you on this material. I'm just going to weave it into my other tests to make sure you have these skills. So I took one of the amazing IB level questions straight out of the textbook rather than assigning it for homework, and I'm going to do it for you in the notes. And I'm trying to walk you through the process of how you're supposed to do these questions where your job is to find the value of an unknown constant. Okay. This cubic polynomial, which has 4 unknown constants, touches, oh, that's telling me something right there. It touches the line y equals 9x plus 2, super important, at this point, okay. We also know that this curve has a stationary point there. Okay. Believe it or not, we were just told 4 very important facts. You might not have seen them all or realized what they all were, but here we go. And I'm going to list them. I'm going to have a bulleted list, but I'm just going to tell you what I know now. The fact that it said that it touched the line tells me that line is tangent to this curve. And it's happening at this x value, 0. Oh, and that's the y value that I get when I plug in x equals 0. Well, they just handed us d, but don't worry, I'll get to that in a second. So anyway, tangent to this curve. Well, when you're tangent to a curve, that means that that line has the exact same slope as the curve. This line has a slope of 9. That means when x is 0, the slope, aka gradient, aka derivative of p of x, is equal to 9. I also know that p prime of x, the derivative, equals 0 at x equals negative 1. And then, of course, I was also handed this y value that goes along with it. So I was told a lot of information. So what do we know? We know, and I don't expect you to write the we know kind of stuff when you're doing the work, but these are all of the clues. Your job is to be the math investigator. What do we know? We know, first bullet, 0, 2, and we also know that negative 1, negative 7, I'll get it right one of these days, are on p of x. So there we go. We have 2 x comma y's on our curve. What else do we know? We know that f prime of 0, meaning, not f, my apologies, p, I just threw my pencil. P prime of 0, meaning if I plug 0 into my first derivative, I get 9. Why? Because tangent has slope, I wrote lope, has slope equal to 9 at x equals 0. See, we're tangent at x equals 0 with this line, which means this slope is this thing's slope at this x value. We also know that, I was going to write f again, when we plug -1 into our derivative, we get 0, and we know that because we are stationary at x equals -1. That is 4 different facts, and I'm going to use them in this order. This one first, and then this one. I'll then come back to this one, and lastly, this one. But Mr. M, how would I have known to do them in that order? You wouldn't have, okay? I know to do them in that order because I worked this question ahead of time and I wanted the notes to be good, all right? You would just use the knowledge and piece it together as you went, like I did the first time I did the question. All right. Fact number 1. P of 0 should equal 2. Well, if you plug in 0 everywhere P has an X, 0, 0, 0. Okay, so 0 plus 0 plus 0 had better equal 2. Plus D, excuse me, had better equal 2. I guess we know D equals 2. All right, well, that was pretty darn simple, wasn't it? So fact number 1 told us that D equals 2. All right. Let's work with clue 2. P prime. Well, I guess we'd better find P prime, huh? So P prime of x, and we're just going to use our power rule everywhere we see exponents, gives me 3ax squared plus 2bx plus c. Now it's time to use the clue. If you plug in 0 to this, you get a value of 9. Okay, 0 plus c equals 9. I guess we know c equals 9. So the first two were pretty darn easy, weren't they? All right. In order to pull off the rest of this question, we are going to have to work with systems of equations. So in order to start clue 3, I need to write P of x with the two unknowns now in them. I have ax to the third plus bx squared plus 9x plus 2. And I'm going to plug in -1. I know if I plug in -1 as an x, -7 is my y. So -7 equals, and now everywhere there's an x, I'm going to drop a -1. A times -1 cubed plus b times -1 squared plus 9 times -1 plus 2. Notice this has an a and a b, two unknowns. The only way you can solve for two unknowns is if you have two equations. All right. -7 equals -a plus b minus 9 plus 2. Well, -9 plus 2 is actually -7. So if I just add this 7 over here, I get 0 equals -a plus b. Oh my gosh. A equals b. Whoa. So whatever A is, B is. Whatever B is, A is. Last clue. Clue 4 gave us a point on the derivative. So we can plug in -1 into the derivative and it will give us 0. Powerful stuff, folks. Okay, so again, we have our derivative right here. Let's see what happens when we plug in -1, and we know it's going to equal 0. We're using this as a y value here, this is an x value here. So 0 equals 3a -1 squared plus 2b -1 plus, and by the way, c is 9, so plus 9. I don't need to say, where am I at? Right here. I don't need to say plus c, because I know c is 9. See? Okay, we get 0 equals 3a minus 2b plus 9. And remember, A equals B. So that means B equals A. That means I can actually write it like this. 3A minus 2A, since they're the same, they're interchangeable, plus 9. So 0 is A plus 9. A is negative 9. B must be negative 9 because they're the same number. And there you have it. P of x equals, there's a lot of 9's, negative 9x to the third minus 9x squared plus 9x plus 2. Mic drop. Now I know it was a long set of notes. I hope you were able to stay with me the whole time. I expect you guys to ask me questions on the homework on a Zoom. What homework? Ha! You thought I forgot. Please. It's on the back. There you go. I'm going to go ahead and give you a clue. You need to use a double angle identity, and you need to factor f prime when you do 12f. So you have to use a double angle identity and then factor on f prime. That's your clue. Yeah, 14.4. All right, everybody. I'll be talking to a lot of you, I hope, soon on a Zoom meeting. Talk to you then.